Hello, my name is Andrew Geary, and welcome to Seismic Sound Off, in-depth conversations in applied geophysics. I am joined by Baishali Roy, a member of the Leading Edge Editorial Board. Baishali served as the Special Section Coordinator in the March 2017 TLE issue for Data Analytics and Machine Learning. Baishali joined ConocoPhillips in 2000. She currently leads a multidisciplinary team for technology development and application of fiber optics technology. Baishali discusses the use of data analytics and machine learning in geophysics next. Yeah, so before we kind of get into the papers and the special section on data analytics and machine learning, I just wanted to make sure the listeners would be on the same page and see if you could just provide a brief overview of what you mean when we're talking about data analytics and machine learning.
Data analytics, big data, machine learning, whatever you call it, is the science or mechanism by which we are trying to harness a huge database that could be coming from different types of applications or different types of measurements. And it's a platform by which we try to find or extract or classify or predict or use it as a predictor for some of the problems that we work with. So we try to harness as much we can from the data to get to the solutions that we would like to. And sometimes this is not easy. Sometimes it's not easy by a human eye to be able to do this kind of assimilation. So data analytics is a framework. It's a set of tools that can be used to achieve this kind of solutions. And I think it's equally applicable to many different fields. And here we are in the field of geophysics, geoscience, and petroleum applications where we're trying to harness this particular tool.
So Mike Davidson writes in the introduction how other industries are utilizing data analytics and machine learning to solve the growing complexities in their own fields. And he writes that the oil and gas industry has been a little slow in adopting these new approaches. So how do the articles in this special section utilize these new tools of data analytics and machine learning to address specific industry challenges?
Yeah, that's a very good question. And first of all, I'd like to thank you for the opportunity to speak as well. We were very pleased with the response we got for the special issue, and we think this is just the beginning of a new technology application. And there's you're going to see a lot more in the future. But going back to your specific question about the comments made by Michael Davidson, the special section includes various examples of machine learning, and I think this is the beginning, but it goes all the way from analyzing potential field data for exploration, which we have done, as geophysicists, we have done over many decades, but it's an opportunity again where you're combining with other data sets. And it goes off to automatic fault detection in seismic data. I mean, that is like one of the core things that an interpreter, a geophysical interpreter, has to do for their day-to-day interpretations. And it shows how you can use machine learning. And then we have papers that talk about accurate estimation of gold reserves or gold resources using different data types. And then applications to reservoir monitoring, or like the 4D application and data management. So it's a wide variety of problems. And as I say before, it is an opening of a door to many such applications, and there could be way more in the future.
Aurelio Polo and his co-authors propose a fascinating future where the entire imaging workflow could be bypassed and faults detected directly from field data, eliminating expensive computer resources and domain expert time. How does this paper use machine learning to demonstrate this possible future?
At its core, machine learning is employed for problems where it might be difficult to explicitly code all the potential rules that need to be followed. Now, we try to use our human mind to do it, but sometimes that's not so transparent. Instead, they develop more general learning algorithms and show the computer examples of input data and sometimes labeled examples of what we want the computer to find or what we want to accomplish. For example, in a computer speech translation like Google, a machine learning algorithm might be fed sound along with a correct translation. And it's a training exercise. We train the computer to learn from given examples. So in the Araya Polo paper, a suite of example Earth models were generated with known fault locations and synthetic seismograms generated to simulate what would be recorded in the field. The algorithm then had many examples of raw seismic data along with known fault locations, and it could learn how to translate between them without the need for seismic migration. So it's a prescription from how you can go from a minimally processed data to an interpretation product, which is remarkable. And given that such ideas may take more effort and time to get into the mainstream, but it's like the start of a new generation of workflows. And I think that's what's remarkable about the Araya Polo paper.
You know, dealing with large volumes of unstructured data is a challenge in many fields. Blinston and Blondell proposed using machine learning techniques to help structure this unstructured data and help lead to better decision making. How did they show machine learning providing a cost-effective solution in dealing with this problem?
Yeah, this is actually an amazing problem that we in the industry, like whether it's petroleum or mining or whatever industry, we have data from the last 50 years, let's say. There's data like ranging from well log data to maps to cultural data to many different types of data. And it is really a lot of work for a human interpreter to assimilate all of that into a product that could be used for, let's say, exploration and identification of prospects and so on. So most of us are familiar with optical character recognition to turn images such as well reports into text. Now, their paper applies machine learning to the organization and analysis of these large, often messy data sets. They're like all over the place by taking a taxonomy developed by subject matter experts and applying machine learning to a group of data sets together automatically without a human manually inspecting them. Now, I would say that this is the first step. I think a domain expert or a geoscience interpreter should still go and do their assessment of the quality of the machine learning. But I think a lot of the front-end work can be done by a machine, which is a huge benefit to the overall cycle time for any workflow.
You know, going to your article that you co-authored with June Cao, you show that machine learning can greatly improve efficiency and reduce the cycle time of quantitative 4D interpretation. Could you share how using synthetic data and machine learning increase the accuracy in predicting the reservoir properties?
Yeah, I'd like to first start off by kind of saying what the problem here was. So in a lot of our field development decisions or reservoir management decisions, we collect lots of data, and 4D is one such data type. You know, we have areas where we have multiple seismic surveys over multiple times trying to understand many different reservoir property changes. And over the years, we have tried to do manual interpretation, one seismic survey at a time, to be able to make these decisions. And as we build up our database, that gradually becomes almost very difficult. So in this paper, we used a synthetic data set to demonstrate that machine learning methods can be equally useful in solving complex, nonlinear, multidimensional physics problems that we encounter every day. So the applications are not limited just to data management, but actually it can solve physics problems that we were unable to solve before. So the physics in this case was very complex, and traditional optimization processes or inversion-based processes often become very ill-posed and under constraint and very computer-intensive. It's even more complex when we need to integrate cross-discipline information such as geoscience, reservoir engineering, production, completions, and we don't all speak the same language. So however, if we can find a way where we can harness the power of all these data types, which has the physics embedded, the data has the physics embedded in them, it opens up a whole new door to solving such problems. And in this paper, our first step was to do a proof of concept through a synthetic case study. And the data shows and the results show that this is an equally effective tool. So we have now actually gone forward and applied the workflow to a lot of field data. and we've gotten very promising results.
What do you hope the readers of your article take away?
I hope the readers understand that this is another tool set in their toolbox. Machine learning approaches for GNG or reservoir engineering problems have been subject of skepticism, particularly because it's often treated as a black box and we don't know what exactly is happening inside. I would like the readers to realize that there is a huge explosion of very smart and robust methods that have been developed over the last 5 years in many other industries, but we can use them in our applications, some of which can improve efficiency significantly by replacing the human component with machines. However, it's important to keep in mind that machine learning methods do not replace the valuable human interactions or well-established physics-based workflows. This is not a replacement of domain experts. It's just a complementary tool and that can help minimize the manual intensive components of the well-established workflows. What I would say is that sometimes it helps in extracting more information from data, which historically sometimes is underutilized. I mean, we look at data, but we don't completely utilize everything that the data is telling us. And in addition, it can even enable workflows that were previously humanly impossible.
How widely available are the data analytics and machine learning tools in the industry, especially maybe at a smaller company?
Actually, there are a lot of things online. There are tools and packages that you can buy from very minimal cost. And in addition, there are even tools and workflows and packages that are free of cost. So there are public domain utilities that could be used and is available to everybody. So what I would say is that the expertise is something you have to gain by yourself, but the algorithms and the tools are already there, but in the public domain at free to a minimal cost. So it is accessible to pretty much the whole industry.
Do you see this becoming an essential skill set in the geophysicist toolkit?
I wouldn't be surprised. I think we need to build up success stories, and as those success stories grow, it could easily become a tool set that everybody uses.
What manual processes do you believe could be replaced by automation in the future?
Yeah, I think I kind of mentioned that a little bit before, but once again, data analytics-based tools can be used to automate workflows all the way from exploration teams who are trying to gather as much data, wells, cultural data, seismic data, and they're not always in some organized manner. And also they have to gather all the data to make a prospect, within a certain time. Sometimes there are timelines, there is lease sales, there is some decision timelines for drilling wells, so they have to do it fast. So it can help them. And then it can also go to development teams, and I'm talking about the oil development teams, of course, and there are many other applications also. But development teams who are trying to compile a variety of data, once again, going from geoscience, reservoir engineering, production engineering, to make the development and reservoir management decisions, such as where am I going to place my infill well? Where am I going to drill my next well? How am I going to enhance the recovery of a well? So it can go from in a variety of domains. So if automation can reduce human cycle time to any degree, it impacts cost, which is our bottom line at the end of the day. In addition, the big impact could be just in data management processes, particularly in this digital world, where everything is almost in some form of digital information. How do we organize that data? How do we utilize that data? So it's a variety, it's a range of topics where automation can help.
Why do you think an SEG member or a geophysicist would seek out or should seek out this special section in these papers?
We are all in the business of either finding resources, and we want to do it with reduced uncertainty. This means that we want to look at as much data as possible at with as less time and effort as possible for efficiency purposes. So this whole idea provides an alternative, cost-effective, efficient, robust tools to our scientists and engineers to help make better and faster decisions. It's been kind of demonstrated in other industries, like you go to the defense industry or the bioinformation, IT industry, and here lies an opportunity for the E&P or the mining industry or the environmental industries that the Society of Exploration Geophysics is attached to. So I think they should look into this special section just to get the ideas of the type of applications that are already being thought about and see how they can adopt it for their own problems.
Is there anything else you would like the readers and the listeners to know about this special section in this work?
I would really like to see people read, and any kind of feedback or, ideas, and it generates thoughts and ideas. And forum for discussion of all these is the SCG annual meeting. So what I would hopefully see is that we start having sessions on data analytics applications, workshops on data analytics and applications, and it's just a way to start interaction between the different members of the society to start talking about this. I think that is the next step, and I hope this special session kind of initiates those kind of thinking process.
At scg.org/podcast, you will find the show notes and links to the March TLE. All of the articles for data analytics and machine learning can be found in print or in the SCG digital library at library.scg.org. Subscribers can read the full articles in the SCG Digital Library, and for those currently not subscribed, abstracts for each of the leading edge articles are always free. To learn more about becoming a member or subscribing to the leading edge, visit scg.org. If you enjoy the show, review us on iTunes. Your review helps others find the show. Season 1 of Seismic Sound Off is sponsored by the SCG Wiki, home to hundreds of biographies of key geoscientists, geophysical tutorials, and core content from the science of applied geophysics. Visit wiki.scg.org to learn how you can grow the world's first online geophysics encyclopedia. Original music by Zach Bridges. This episode was produced by Isaac Farley and me, Andrew Geary. Special thanks to Steve Brown, the Leading Edge managing editor. Thank you for listening. This is Seismic Sound Off, signaling off.